This is lecture 4, the simplex algorithm for IE 3340 operation research. The learning objectives for this lecture is to learn how to use the simplex algorithm to solve linear programming models with more than 2 decision variables. So in previous videos, we learned how to solve linear programming models that had 2 decision variables using the graphical method. But as we explained in that lecture, if you have more than 2 decision variables, then the graphical method will not work. So the simplex algorithm is an algorithm that will solve problems, linear programming problems and models that have more than 2 decision variables. In this algorithm, what we learn in linear algebra for the Gauss-Jordan method, we're going to be using the Gauss-Jordan method within the algorithm. But before we get into the steps of the algorithm, we need to learn a few things in order to set up our linear programming models to be in the right format for us to implement the algorithm. So in this first part of this lecture, we're gonna focus on how to set up linear programming models, and also we're gonna learn how the algorithm works. And in the next video, we are going to implement the simplex algorithm. We're gonna go to the steps and we are going to solve problems using the algorithm. But for now, let's learn how to set up the linear programming models, and also let's understand how the algorithm works. So the agenda for this lecture includes the introduction, converting in linear programming to standard form. As I mentioned, how do we set up our linear programming models, or format the linear programming model in a way that we can implement the simplex algorithm. And then we're gonna learn a little bit more about how this algorithm will work. And we're gonna do that using this transition from graphical to algebraic solution. Then we're gonna look at the preview of the simplex algorithm. And in the next video, we're gonna learn how to implement the simplex algorithm. So for our introduction, in the first 3 weeks for this class, we have focused on how to model linear programming models, how to set up a linear programming model, including the objective function, the decision variables, and the constraints. And also we learn how to solve linear programming models that have 2 decision variables. And we solve those using the graphical method. But as I mentioned already, most real-life linear programming models have many variables. So a method is needed to solve linear programming models with more than 2 decision variables. We will study the simplex algorithm, which is used to solve linear programming models with thousands of constraints and variables. So as we discussed in our first video, linear algebra skills are needed now. So they will come into play. And that was our first lecture. So let's start by discussing how to convert our linear programming models to standard form. And as I mentioned already, we need to set up our models. We need to set the models in a specific format so we can implement the simplex algorithm, and then we can solve these linear programming models. So before the simplex algorithm can be used to solve an LP, the linear programming must be converted into a problem where all constraints are equations and all variables are non-negative. A linear programming is in this form is set to be in standard form. Okay, so we want all our constraints to be equations and all variables to be non-negative. So what are the steps? The first step, if the I constraint is less than or equal to or inequality constraint, then we convert it into an equality constraint by adding a slack variable and the sign restriction SI or SI greater or equal to 0. So if we have an inequality of this form, less than or equal to, we are going to convert it into an inequality by adding a slack variable that we are going to name SI, and also adding the sign restriction, making that slack variable positive. If the I constraint is also an inequality but greater or equal to, then we convert it to, so if it is greater or equal to, we convert it to an equality by subtracting an excess variable and adding the sign restriction, making that excess variable positive, greater or equal to 0. If xi is unrestricted in sign, then we replace xi in both the objective and constraints by this substitution, xi prime minus x double prime I, where xi prime is greater or equal to 0 and xi double prime is also greater or equal to 0. So let's look at one example. We have company Leather Limited that manufactures two types of leather belts, the deluxe model and the regular model. Each type requires 1 square yard of leather. A regular belt requires 1 hour of skilled labor, and a deluxe belt requires 2 hours of skilled labor. Each week, 40 square yards of leather and 60 hours of skilled labor are available. Each regular belt contributes $3 profit, and each deluxe belt contributes $4. We're going to write an LP, or linear programming, to maximize our profit. So the decision variables are 2. X1 equals number of deluxe belts to be produced weekly, and X2 is equal to the number of regular belts produced weekly. The LP is then the maximization of the profit, and we know that we make $4 per deluxe belt, so it's 4 times X1, and we make $3 for the regular belts, so 3 times X2. And then we have two constraints. One is the material, and the second one is the labor. So this is our LP. You see the constraints are less than or equal to, because we have up to that much material. We don't have to use it all. We don't have to use it all. And also we also have a limit in terms of the labor constraint. So those hours are available, but in order to maximize our profit, we don't necessarily have to use the whole thing. So to convert the leather and label less than or equal constraints to equalities, that's what we want to do now. We want to transform these LP into standard form. So we are going to follow these steps. So in our case, we had these inequality. So we want to make those inequalities equalities. So let's do that. So to convert the leather and labor constraints to equalities, we define for each constraint a slack variable, SI. So we're going to have a slack variable for each inequality. So let's say for inequality 1, we're going to have S1. For inequality 2, we have S2. A slack variable is the amount of the resource unused in the ith constraint. So what that means is if you have this constraint right here, let's say this constraint, I'm gonna write it here, x1 plus x2 less than or equal to 40. And let's say you get to use, let's say 15 and 15 jars of leather in your optimal solution. So that's gonna be 30, which is less than or equal to 40, okay? The purpose of the slack variable is to tell you how much material was left unused in this case. So if you formulate or you write this as in a standard form, you have x1, x2 plus s1 equal to 40. If you end up using 15 plus 15, in order to make this equal to 40, you will get 10, right? So the decision, this decision variable is telling you, you know, at the end, in your optimal solution, the slack is equal to 10, which means that that's the amount of material that you didn't use in your solution. So we are getting the same solution by making the problem to standard form, but we can gather additional insights with those decision variables. So this LP is not in standard form. So the same LP in standard form can be written as follows. The objective function is not going to change, but the constraints are going to become inequalities now, or I mean equalities now. So we're going to add a slack variable for the first constraint. So x1 plus x2 plus the slack variable s1 is going to be equal to 40. Then we have another slack variable for the second constraint, 2x1 plus x2 plus the slack variable for the second constraint, use a different name, s2, is equal to 60. So those are the constraints. And now we have to remember that we have to make those decision variables greater or equal to 0. I'm sorry, this should be correct. So this is S1 and S2. All of them have to be greater or equal to 0. So that's how you formulate this problem into the standard form. Let's look at another example. In the next example, we're going to have constraints that are greater or equal to 2, greater or equal to something. So we have the LP Dorian auto example. This is coming from a previous lecture. So we formulated this problem. Now we want to transform this LP to standard form. So in this case, we have inequalities that are greater or equal to something. So if we go back to the instructions here. When that's the case, then we are going to convert those equations into equalities by subtracting an excess variable and adding the sign restriction EI greater or equal to 0. So let's do that. So we are going to transform the auto LP to standard form. So our problem is a minimization problem. Minimize Z equals to 50 x1 plus 100 x2. And then we have two constraints. So this is subject to 7 x1 plus 2 x2. In this problem, we are going to subtract an excess variable for the first constraint, so minus E1 equals 28. For the second constraint, we had 2x1 plus 12x2 minus E2 is going to be equal to 24. And then we have the decision variables x1, x2, again, E1 and E2 being greater or equal to 0. So the excess variable does the same or is used to model the kind of what we did for the slack variable. So, but we have to subtract it because it is going to show that amount of the resource that we were not able to meet, right? So let me show you. So this is 7x1 plus 2x2, which is the constraint, greater or equal to 28, right? So what this constraint is saying is whatever you have in this side has to be greater or equal to 28. But let's say that for some reason you cannot achieve that amount. Like you get 1 and 1 here, so that's going to be equal to 7 plus 2, which is not greater or equal to 28, right? It's not, that's not the case. But if we use an excess variable, 2x1 plus 2x2 minus e, 1 equals 28. Actually, you have to meet this. So let's say that this cannot be this. You have to meet this amount. So let's say you have 7 and 2 here. So you end up with 21 plus, let's say this is 5. 21 plus 10, that's 31, which is greater or equal to 28. So if you have now an excess variable, you can use this amount to quantify how much is the excess, right? So this is 21 plus 10. For this to be 28, this has to be minus 3 equals 28. So that excess variable, basically what it's saying is, you know, you were able to satisfy the constraint, but you were above that amount by this much. So in this case, we were talking about in this problem, being able to reach out to specific population. So if you go above that 28, means that you were able to reach out more than that, right? You more your campaign was able to reach out more population than you expected. And if you want to know how much more, then you can use that excess variable to quantify that amount. So in this case, it's 3 more. Okay, so that's how the excess variable works. You identify the type of constraints you have, you subtract an excess variable if your inequality is greater or equal to something, and then you model that in your standard form for the LP. But the important thing here is that you know how to make this problem or how to convert this problem into a standard form, which is right here. Okay, so now we have a combination. We have an LP that has inequalities of different forms. So we have less than or equal to and greater or equal to. So we want to transform this into standard form. So if we follow the same steps, want to maximize Z equals 20 x1 plus 15 x2, and this is going to be subject to x1. So this is a less than or equal constraint, so that means that we add a slack variable equals 100. Then we have x2 plus slack variable number 2 also equals 100. And then we have 50 x1 plus 35 x2. This is also less than or equal to, so we add another slack variable, S3 equals 6,000. And then we go to this one, which is a inequality greater or equal to. So we have to subtract an excess variable. So it's 20 x1 plus 15 x2 minus E. Now, the way you name this, if you use the index of the constraint, so this is constraint 1, constraint 2, constraint 3. So this is going to be constraint number 4. Then you can use E4 here. But the name is not important. As long as you have a different name for each constraint, then you'll be fine. What you cannot do is to have the same slack variable in constraint 1 and constraint 2. You see, in constraint 1, we have S1. In constraint 2, we have S2, so the name is different. So we subtract E4, and this is equal to 2,000. And then we had to make all these decision variables greater or equal to 0. There's 1, 2, 3, and E4 greater or equal to 0. And that's the standard form for that problem. We have another example. So we want to convert this LP to standard form. The interesting thing about this problem is that we have a decision variable that is unrestricted in sign, meaning that X could be negative or positive, and that when you transform those type of problems into standard form, then you have to take care of those type of decision variables. So in this example, I have a baker that has 30 ounces of flour and 5 packages of yeast. Baking a loaf of bread requires 5 ounces of flour and 1 package of yeast. Each loaf of bread can be sold for 30 cents. The baker may purchase additional flour at 4 cents an ounce or sell the leftover flour at the same price. So you have 2 options for that flour. You can buy more or you can sell the one that you have. We want to formulate an LP to help the baker maximize profits. So the decision variables for this problem are the following. X1 is the number of loaves of bread baked, and X2 is the number of ounces by which flour supply is increased by cash transactions. So remember, you can sell or you can buy more. So the appropriate LP is the maximization of 30x1 minus 4x2. So 30 is the 30 cents that we can we get if we sell a loaf of bread, and minus 4 cents is the amount that you pay for buying more ounces of flour. So your decision: you sell more loaf, or you buy more material, right? So this is buying additional flour, and this is selling loaf of bread. So that's your objective function, and that this is subject to the flour constraint. So baking a loaf of bread requires 5 ounces of flour. So these are the 5 ounces of flour. And then X2 is the number of ounces by which the flour supply is increased. So per loaf of bread that you sell, you have to buy or have this much flour, and then you have the decision of whether you're going to buy more flour or you're going to sell the one you have. You know, x1 has to be less than or equal to 5, because you have 5 packages of yeast, so you want to make sure that you use them. And then, so that's a constraint, and you require one per loaf of bread, right? So you can bake as many as 5. That's how many loaf of bread you can bake. So now, if you have that constraint, your decision is if you are going to, how many loaf of bread you're going to bake, and if that flour that you have is enough, and if you have some left, are you going to sell it? Or if you don't have enough to bake those 5, are you going to buy more? So those are the decisions. So note that x2 is greater than 0 if x2 ounces of flour, were purchased, and x2 is less than 0 if x2 ounces of flour were sold, and x2 equals 0 if no flour was bought or sold. Okay, so this decision variable x2 can be 0, can be positive, and can be also negative. So this decision variable is unrestricted inside. So is when you define that in the formulation, you make x1 greater or equal to 0, but that decision variable in particular has no bounds. It could be negative, positive, or 0. So how do we transform this into standard form? If you remember, for our discussion on slide 7, if the variable xi is unrestricted in sign, then we are going to, so this 0.3, we replace xi in both the objective and the constraint by this. And then we make those prime, xi prime and x double prime I, positive or greater or equal to 0. So if we go back here, converting this into standard form, we are going to do the following substitution. So x2 now is going to be transformed to x2 prime minus x2 double prime. So I'm going to substitute that into the LP, and then I'm going to also add the slack variables in this case, since these are inequalities less than or equal to something. So let's do that. So we are going to maximize Z, which is equal to 30 x1 minus 4 x2 prime plus 4 x2 double prime. So in this piece, I'm doing this substitution. So anywhere where x2 is, I'm going to substitute that by this. And this is going to be subject to 5x1 minus x2 prime minus x double prime 2 plus my slack variable 1, and this is going to be equal to 30. For the second constraint, I have x1 plus s2 equal to 5. And then I have my decision variables. Now all of them can be greater or equal to 0, x1, x2 prime, x2 double prime, s1, and s2, all of them greater or equal to 0. So I show you how to transform a linear programming model into standard form. And we saw and we explained different cases, the cases in which you have less than or equal constraints, the cases in which you have greater or equal to constraints. And this final example is a combination of that, plus we are adding the challenge of how to deal with these unrestricted in-sign decision variables. So in this last example, we have a variable that is unrestricted in sign. So we have to do the substitution for those decision variables. Plus, when we transform this into standard form, we have to add the slack variables. So now we are going to transition to the next topic of this lecture. And this is, how do we transition from the graphical to the algebraic solution? So the development of the algebraic simplex method is based on ideas conveyed by the graphical LP solution. In the graphical method, the solution space is the intersection of the half spaces representing the constraints. In the simplex method, the solution space is represented by simultaneous linear equations and non-negative variables. In the algebraic solution space, defined by m times n equations, m is less than n, basic solutions corresponds to the corner points in the graphical solution space. And as we mentioned in the previous video, we know that in the graphical method, the optimal solution will be a corner or extreme point. So the simplex method does a search for those corner or extreme points and is trying to identify out of the corner points which one is the optimal. These are determined by setting variables equal to 0 and solving the equations for the remaining variables. So this means that the maximum number of corner points is going to be given by this equation, okay, where m equals the number of rows and n equals the number of columns. And in these flowcharts, we have the comparison between the graphical method and the algebraic method. The algebraic method is the base for the simplex algorithm. So the graphical method, we explained that in a previous video lecture. You graph all constraints, including the non-negativity restrictions. The solution space consists of an infinity of feasible points. We identified the feasible corner points of the solution space, and candidates for the optimum solution are given by a finite number of corner points. And then we use the objective function. You remember that iso-cost, iso-profit line. We use the objective function to determine the optimal corner point from among all candidates. In the algebraic method, we represent the solution space by m equations in n variables and restrict all variables to non-negative values. The system has infinity of feasible solutions. We determine the feasible basic solution of the equations, which are the candidates for the optimal solution and are given by a finite number of basic feasible solutions. Then we use the objective function to determine the optimum basic feasible solution from among all the candidates. So consider the following LP with two variables. We are maximizing 2x1 plus 3x2. So you remember, once you graph the the feasible region in this case, once you graph the constraints, you can identify the feasible region. In this case, that's the gray or the shaded area here. You know that the optimal solution is going to be somewhere in that area. But as we explained already, those optimal solutions are found in the corner points. So what we did to find our optimal solution is that we graph the objective function. Right? We use an isoprofit line in the graphical method. And let's say that optimal or that isoprofit line is something like this. Then let's put it here. So let's say that our isoprofit line can be drawn using this 2 points. Then we use that isoprofit line to find, as we move the line parallel to it, until we touch the last point in the feasible region, then we can identify the optimal solution for the problem. Okay, so that's the way we find the optimal solution using the graphical method. But now we're going to use this algebraic method, which is based for the simplex method, and we are going to find the same result without having to graph the constraints and or graphing the problem. So consider the following LP with 2 variables. Algebraically, the solution space of the LP is represented by the following equations and variables. So you can see now, we have put that problem into standard form. We have added 2 slack variables. The basic solutions are determined by setting n minus m variables equal to 0 and solving the remaining m equals 2 variables. So m, again, is the number of rows, and n is the number of variables. So how many decision variables we have? We have 4, right? X1, X2, S1, and S2. So 4. And how many rows or constraints? We have 2 constraints. So M equals 2. So for example, so we are going to, basic solution are going to be determined by setting m minus 2 variables equal to 0. So we're going to set up 2 variables equal to 0 and solving for the remaining 2 variables. So for example, if we set x1 and x2 equal to 0, the equations provide the unique basic solution equals to s equals 4 and s2 equals 5. This corresponds to point A in the graphical representation. So that would be S1 equals 0, S1 equals 4, X2 equals 5. Those are not aces in this. But when we know these are the values that we can graph, X1 equals 0, X2 equals 0. So in the graphical representation, that will be this point. So this solution corresponds to point A. Another point can be determined by setting S1 equals 0, S2 equals 0, and then solving the resulting 2 equations. So if we do that, we can solve these because we have 2 equations and 2 decision variables. The associated basic solution is x1 equals 1, x2 equals 2, and that solution corresponds to point C. You probably are wondering which variables should be set equal to 0 to target a specific corner point. Without the graphical solution space, we cannot specify m minus n0 variables associated with a given corner point. So the solution considers all combinations in which variables equal 0 and solve the resulting equations. The optimal solution is the basic feasible solution or corner point with the best objective value. Non-basic variables are the 0 and minus n variables. The remaining variables are called the basic variables. The solution obtained by solving the equations is referred as to the basic solution. So consider the following LP with two variables. So if we go to the process of finding all possible combinations of making two of them equal to 0, so these are all possible combinations. We have 6. So we are making, in every combination, we're making this. So for the first combination, we're making x1 and x2 equal to 0. These are going to be the basic variables or the non-zero variables. And the solution for S1 and S2 is 4 and 5. The associated corner point is going to be this one. And is this visible? Yes, because it's part of that gray shaded area. What will be the objective function value? Well, if you substitute S1 and S2 into the objective function, you don't have those coefficients, those decision variables there. You do have this. And you know that when they are 4 and 5, then x1 and x2 equals 0. So by substituting 0 here and 0 here, the objective function value is equal to 0. Let's look at the next one. So if we make x1 and s1 equal to 0, then my basic variables are going to be x2 and s2. So I'm solving for x2 and s2. So, so let me show you what that means. So for this equation is 2x1 plus x2 plus s1 equal to 4. And then we have x1 plus 2x2 plus s2 equals 5. So basically what I'm saying for this case, the second case, is that I'm making x1 equals 0 and I'm making s1 equals 0. Right, so if that's the case, then the first constraint is going to become x2 equals 4. And the second constraint is going to be 2x2 plus s2 has to be equal to 5. So if I substitute x2 here, then I have 8 plus s2 has to be equal to 5. So s2 has to be minus 3. So these are the values that we have right here. Okay, so I have x2 equals 4 and x1 equals 0. I can plot that number into the graph. And that point is this point right here. Is point F. Is this visible? No. So we don't have an objective function value. And you can follow the same process for each one of them. Like if we make x1 and s2 equals 0, the basic variables are going to be x2 and s1, and the solution for x2 and s1 is going to be 2.5 and 1.5. The associated point for that one is this one. Is part of the feasible region, yes. So you can substitute x1 in this case. You will make x1 equals 0 and x2 equals 2.5 into the objective function. And that's going to give you this objective function value. The process continues till we get to the last point in which we make non-basic variables s1 and s2 and the basic variables x1 and x2. So the basic solution is 1 and 2. That's point Z, this point, which we know is the objective function, the optimal solution. It is feasible. And then the objective function value, when you substitute 1 and 2 into the objective function, is going to be equal to 8. So at the end, once we study all possible combinations and we get all the possible values for the optimal solution, then we can compare. Since we are maximizing, we know that we are looking for the largest value. So out of these numbers, the maximum value is going to be 8. So what that tells you is that the optimal solution is 8, and that happens when x1 equals 1 and x2 equals 2. So we can follow this algebraic method to identify the corner points using non-basic and basic variables. and then we can find the objective function value, the corresponding objective function value for each one of the combinations. And once we find all of them, we can find the one that is maximizing or minimizing. In this case, was maximizing our objective function. So we are looking for the largest value to identify the optimal solution. Okay, so let's talk a little bit about the preview of the simplex algorithm. So the general form for an LP, suppose that an LP with m constraints and n variables has been converted into standard form. The form of such an LP is here. So we have all decision variables and all constraints are equalities, and all decision variables are greater or equal to 0. If we define that problem into a matrix form, we have the matrix A for the coefficients, we have the decision variables vector, and we have the right-hand side vector. The constraints may be written as a system of equations AX equals B. Consider the system AX equals B of m linear equations in n variables. A basic solution to AX equals B is obtained by setting n minus n variables equal to 0 and solving for the remaining n variables. This assumes that setting n minus n variables equal to 0 yields a unique value for the remaining n variables. To find a basic solution to AX equals B, we choose a set of n minus n variables, the non-basic variables, and set each of these variables equal to 0. Then we solve for the values for the n minus n variables, which equals m, the basic variables that satisfy AX equals B. Different choices on non-basic variables will lead to different basic solutions. So example 5, consider the basic solutions for the following system of two equations: x1 plus x2 equals 3 minus x2 plus x3 equals minus 1. The number of non-basic variables is going to be equal to 3 minus 2. So we have three decision variables and two equations. So 3 minus 2 equals 1. Setting for example non-basic variable x3 and basic variable x1 and x2, we get the following. So we can obtain the values of the basic variable by setting x3 equals 0. Solving, we find that x1 equals 2, x2 equals 1. Thus, x1 equals 2, x2 equals 1, and x3 equals 0 is a basic solution. If non-basic variable is x1 and the basic variables are x2 and x3, the basic solution becomes x1 equals 0, x2 equals 3, and x3 equals 2. If we choose x2 as the non-basic variables, then we have x1 and x3 as the basic variables. Then the basic solution becomes x1 equals 3, x2 equals 0, and x3 equals minus 1. Some set of n variables do not yield a basic solution. Consider the following linear system. If the non-basic variable is x3 and the basic variables are x1 and x2, the corresponding basic solution will be this equation x1 plus 2x2 equals 1, 2x1 plus 4x2 equals 3. Since this system has no solution, there is no basic solution corresponding to x1 and x2 being the basic variables. Any basic solution in which all variables are non-negative is called a basic feasible solution, or BFS. For the basic solution on the previous slide, x1 equals 2, x2 equals 1, and x3 equals 0, and x1 equals 0, x2 equals 3, and x3 equals 2 are basic feasible solutions. x1 equals 3, x2 equals 0, and x3 equals minus 1 fails to be a basic feasible solution because x3 is less than 0. Adjacent basic feasible solutions. So for any LP with m constraints, two basic feasible solutions are said to be close or adjacent to each other if their set of basic variables are n minus 1 basic variables in common. Note that two basic feasible solutions are adjacent if they both lie on the same edge of the boundary of the feasible region. So for example, in the leather limited LP, the basic feasible solutions corresponding to point E is adjacent to the basic feasible solution corresponding to Z, of these 2 points. They share or they're next to each other, connected by that line. These points share n minus 1 equals 2 minus 1 equals 1 basic variable, x1. Point E, the basic variables are x1 and x2. And for F, basic variables are s1 and s2. Are not adjacent. So this E and F, you see they're across each other. They're not adjacent since they don't share basic variables. So for this problem, if we go through the same process as we did for the previous example, we can identify the basic variables, the non-basic variables, the basic feasible solution, and the corresponding point to corner based on this graph. Okay, so we're gonna get up to here. In the next video, we're gonna start discussing the steps of the simplex algorithm. So